Hello students, welcome to my YouTube channel. Today in this video we are going to discuss the various types of boundary layer thickness. So without wasting our time, we will start with a video lecture. In our last lecture we had discussed what is boundary layer, how the formation of boundary layer take place. In this video we are going to discuss the four types of boundary layer thicknesses, that are nominal thickness, the displacement thickness, momentum thickness and energy thickness. So boundary layer thickness. Boundary layer thickness or nominal thickness, it is simply defined as the distance perpendicular to the surface, where the value of the local velocity becomes 99% of the free stream velocity. In our last lecture, we had already defined the boundary layer. So inside the boundary layer, the continuous variation in velocity, it is taking place from surface up to 99% of its value, and outside the boundary layer the value of the velocity is equal, which is equals to the free stream velocity. Now in order to understand or revise it again, consider this is the x direction. Now suppose the flow is taking place in x direction and the free stream velocity is u infinity. Now consider this as y direction. So the no slip condition, it will exist near the surface area. So here the value of velocity u becomes 0. Now as you move away from the surface, the value of this velocity will going to increase, and after a particular distance, we will say consider this distance del. Now at this point the value of this velocity will become 99% of the free stream velocity u infinity. Okay, and outside this thickness the velocity is constant, which equals to u infinity. So this distance in y direction from the surface, where the value of velocity is 99% of the free stream velocity, this is called as boundary layer thickness or nominal thickness, denoted by del. Now this boundary layer, basically this thickness of the boundary layer, it continuously changing along the x direction. So this boundary layer thickness, or simply nominal thickness del, it is a function of x, as well as it is a function of Reynolds number. Now we already know Reynolds number, it is nothing but it is a product of velocity into distance x divided by kinematic viscosity nu. So this Reynolds number is directly proportional to x. So as you move away from the leading edge, as the value of x increases, the value of uh, nominal thickness del increases. So you can see in the diagram that uh, uh, as now you can also see in this diagram, as we are increasing in x direction, so the value of del, it is increasing along y direction. We had also discussed the boundary layer region. It is divided into three regions. First is laminar region, second is transition region, where the flow is transiting from laminar to turbulent, and the third region is turbulent region. So the value of this or the relation for finding this nominal thickness del, it will again depend on whether the region is a laminar region or turbulent region. Now, the thickness of boundary layer in the laminar flow region or laminar region, it is given by Blasius, and the equation is called as Prandtl-Blasius equation, which is given by del equals to 5 into x upon Reynolds number at a distance x. Here, this x represents the distance from the leading edge. So when del equals x equals to 0, that means at x equals to 0. So from this equation, del equals to 0. So basically, uh, the thickness of boundary layer at the leading edge, it is always 0. So at x equals to 0, del is always equals to 0. And as the x increases, okay, the value of del increases in y direction. Okay. Okay, after that, for turbulent flow or in turbulent region, it is again given by Prandtl-Blasius equation, and that equals to 0.377x upon Reynolds number to the power 1 upon 5. So using this equation, you can find out the thickness of nominal thickness in turbulent region. After that, we are going to discuss the displacement thickness. So the displacement thickness of a boundary layer is simply defined as the distance perpendicular to the surface. That means it will be again the distance in y direction, such that the plate should be moved, or this stationary plate, it should be moved to compensate for the reduction in flow rate or reduction in discharge due to boundary layer formation. Okay, so in order to understand this definition, consider the case when suppose the fluid is flowing with a velocity of capital U, and suppose this plate is absent. Okay, so in that case, the entire velocity of this flow passage would be constant, and that equals to capital U. But due to presence of boundary layer, we know the no slip condition exists near the surface, so velocity is zero near the surface, and this velocity is slowly increasing in y direction. Okay, so because of that, in this region you can see this blue region, so in this region the velocity is less, so this region represents u, capital U minus small u. Okay, so this capital U minus small u, it is called as velocity deficit. So this velocity deficit, it is nothing but the amount by which the velocity has been reduced. So due to the reduction in the velocity, we know the discharge, which is the product of velocity and cross section area, where area is nothing but area of flow. So area of flow is same in both the cases, but when the plate is absent, so the in the same area the velocity is capital U, and when the plate is present, so basically there is a reduction in velocity which is equals to capital U minus small u. So basically there will be a reduction in discharge or reduction in flow rate. So whatever the reduction in flow rate due to boundary layer formation is taking. So in order to compensate that much, okay, how much is the value you are supposed to move this plate in y direction? So that distance by which you are supposed to move this plate in y direction, that is called as displacement thickness, denoted by del star. So again, quickly we will see the definition. So the displacement thickness of a boundary layer is simply defined as the distance perpendicular to the surface, okay, or it will be the distance in y direction by which the plate is supposed to move to compensate for the reduction in flow rate due to boundary layer formation. This displacement thickness, denoted by del star, it is given as integration 0 to del 1 minus small u by capital U into dy, where small u, it represents the velocity at a distance or at a given instant of distance y from the surface. Okay, after that we are going to see the derivation of this nominal or displacement thickness. So consider a free stream velocity which is moving with a velocity capital U. Now consider a plate, then due to this presence of, or due to the interaction of this free stream velocity along the plate, there will be a formation of boundary layer which is as shown in the figure. Consider any section, which is denoted here at a distance x, from leading edge. Okay, at a distance x from leading edge, let at this point the uh, nominal thickness is del. Okay, after that we are going to consider, along this passage we will consider any elementary strip of thickness dy. We are going to consider any elementary strip of thickness dy at a distance y from leading edge. So all this information is given in this diagram, and we are also going to assume the width of the plate as unity. Okay, so if we talk about this strip, if we are going to talk about this strip, so for this strip the elementary area of this strip will be, its width is unit quantity, so we will say 1 into dy, and we will say let u be the velocity at this point, at this distance y, its instantaneous velocity is u. So mass flow rate through the strip, so that mass flow rate, as per our continuity equation, it is given by rho into u into dy into 1. It is rho into velocity into cross section area. Now in this case our area is 1 into dy, so it is simply rho u dy. Okay, so the mass flow rate area is rho u dy. Now suppose this plate is absent. Suppose this plate is absent, so in that case the velocity of flow from the entire passage of flow, it would be capital U. So in that case the mass flow rate area would have been rho into capital U into dy. Due to presence it is rho into small u into dy. Due to absence it would have been rho into capital U into dy. Okay, so the reduction in mass flow rate area, it will be the mass flow rate area due to absence minus mass flow rate area due to presence of the plate. So it will be rho into capital U minus small u into dy. Now this much is the reduction of mass flow rate area which is taking place only through a small strip. Now in order to find out the total reduction in mass flow rate area, we are going to integrate this entire equation. Now our limits will be from 0, because we know basically we are going to measure the distance from the surface, and this much reduction it will going to take place for the thickness, nominal thickness del. Okay, so we are going to integrate it from 0 to del rho into capital U minus small u into dy. So basically this term represents the total reduction in mass flow rate area which is taking place. Now, but as per the definition, we had already defined that this reduction in area which is taking place. Okay, 1 minute. Okay, this reduction in area which is taking place. Okay, this should be equals to the reduction in mass flow rate area which have been taking place by moving this plate in y direction. That means by moving the plate by the thickness or by the distance which equals to displacement thickness del star. Therefore, the reduction in mass flow rate area as per our definition, it should be equals to rho into capital U into del star. So basically these two terms, okay, these two terms, integration 0 to del rho into capital U minus small u dy, it should be equals to rho into capital U into del. So we can equate these two terms. Finally rho will be cancelled from both sides, and we can divide this capital U on left hand side. So we will have del star equals to integration 0 to del 1 minus small u by capital U. So basically this will be our equation for calculating the displacement thickness del star. I hope you might have understand this derivation, because the derivation is really simple, but you are supposed to understand the concept behind this derivation. Okay, so you are going to understand that if you understand the definition of displacement thickness. Okay, so after displacement thickness we are going to see our next term, which is momentum thickness. So almost the concept is same, the derivation is almost similar. The momentum thickness is simply the distance perpendicular to the surface by which the surface should be moved in order to compensate for the reduction in momentum. Here only the difference is we are going to compensate for the reduction in momentum of the flowing fluid due to presence of boundary layer. It is given by the Greek symbol theta, and mathematically it equals to theta equals to integration 0 to del small u by capital U into 1 minus small u by capital U into dy. And the concept is same. If there is a formation of boundary layer, so basically here there will be a velocity deficit which equals to capital U minus small u. Okay, and if we are neglecting this velocity deficit, so defect, so in that case basically our entire flow passage velocity would have been capital U. So due to presence of boundary layer, there is a reduction in momentum which is taking place. So if you are going to move the plate in y direction, okay, normal to the direction of flow or direction of surface, so in that case the distance by which you are supposed to move this plate, so that distance is nothing but momentum thickness denoted by theta. So similar is the definition, all the concepts are same. Here only the difference is in this definition we are going to consider the reduction in momentum. So quickly we will see the derivation for this momentum thickness. So again we are going to consider the same case. Consider a free stream velocity of the fluid capital U, and consider a stationary fixed plate. Now whenever this free stream fluid moving with velocity capital U, it will come in contact with this plate, there is a formation of boundary layer. Now again we are going to consider any layer or any section at a distance x from leading edge, and let del, it will be the thickness, nominal thickness at that point. Consider any elementary strip of thickness dy at a distance y from leading edge, and let small u, it will be the velocity of flow at that distance y. So the if we consider the unit width of the plate, so the elementary area of the strip is again 1 into dy. Now the momentum of the flowing fluid. Now what is momentum? Momentum, it is nothing but the product of mass flow rate into velocity. So it will be rho u dy, okay, into u. So it will be rho u square dy. So the total momentum is, due to presence of boundary layer, it is rho u square dy. Now suppose for the same mass flow rate, which is small rho into small u into dy, if the boundary layer was absent, so in that case the velocity could have been capital U. So for the same mass flow rate rho small u dy, the momentum could have been rho small u dy into capital U. So basically the reduction in momentum of the fluid due to presence of elementary strip, okay, or due to presence of boundary layer through the elementary strip, it is rho into small u into capital U minus small u into dy. Now remember, this is the reduction which is taking place only for the elementary strip. Therefore for total reduction in the momentum, we are going to integrate it within limit 0 to del. So it is integration 0 to del rho u into capital U minus small u into dy. Now if suppose the boundary layer would have been absent, okay, so in that case the total mass flow rate flowing from that area it could have been rho into capital U into theta, and in that case, in order to find out the momentum, we will multiply it with the velocity capital U. The total momentum could have been rho theta u square. Now here theta represents the momentum thickness as per our definition. Okay, so the these two quantities, okay, due to presence of boundary layer, whatever the reduction in mass flow rate area is taking place, momentum is taking place, as well as this second quantity rho capital U square theta, that means the distance by which or thickness by which the plate should be moved in order to compensate this reduction in momentum. This could have been same. So our left side and right side, you can equate them. So you can divide this row, or you can cancel this row from both sides and divide this u square on right hand side. So finally we will get the equation theta equals to integration 0 to del small u by capital U into 1 minus small u by capital U into dy. So basically this is the equation for finding the momentum thickness. Similarly, the last thickness which we are going to consider, it is called as energy thickness. It is denoted by del double star or del E. Now in order to understand the definition, the same concept is there. The energy thickness, it is simply the distance perpendicular to the surface, okay, or normal to the surface, by which the surface should be moved in order to compensate for the reduction in kinetic energy. Remember, in this case the term will be kinetic energy of the flowing fluid due to presence of boundary layer formation. So it is denoted by del E. So del E is the integration 0 to del small u by capital U 1 minus small u by capital U whole bracket square into dy. So here the concept is same if you have understand the last two definitions. Okay, so here again the concept is same. Due to presence of boundary layer, there will be a velocity deficit. Now we know kinetic energy is 1 by 2 mass into square of velocity. So basically square of velocity deficit will be there, okay, and that should be compensated by moving the plate in y direction. So here whatever the reduction in kinetic energy is taking place, considering capital U constant, So these two values we are going to equate, and basically we are going to derive the energy thickness. So quickly we will see the derivation of energy thickness. So again we are having the same case. Consider a free stream of fluid moving with a velocity capital U. It came across a fixed plate. So there will be a formation of boundary layer, and we will consider any elementary strip at a distance x from the leading edge, and let its uh, nominal thickness is del. Now consider any elementary strip at a distance y uh, from the surface and of distance dy. In this case the velocity is small u. It is a instantaneous velocity at a distance y. Again we are going to consider the unit width of the plate. So in this case the area of the elementary strip will be 1 into dy, and basically in this case the kinetic energy will be 1 by 2 into mass flow rate, which is rho into u into dy into square of velocity u square. So it is 1 by 2 rho u cube dy. Now for the same mass flow rate rho u dy, if we consider the boundary layer is absent, so velocity could have been capital U. So kinetic energy for the same mass flow rate, it would have been 1 by 2 rho into small u into dy into capital U square. Therefore the reduction in kinetic energy through the elementary strip, it will be 1 by 2 rho u into capital U square minus small u square dy. Now remember, this is the reduction through elementary strip. Now in order to find out the total reduction in kinetic energy due to presence of boundary layer, we will going to integrate it from within the limit 0 to del. So the equation is integration 0 to del 1 by 2 rho into small u into capital U square minus small u square into dy. Now, as per our definition of energy thickness, now if you are going to move this plate along y direction by the distance del E, okay, and you are going to consider the velocity u capital U uniform. So in that case, the kinetic energy which will reduce by moving this plate by distance del E, it is 1 by 2 rho into capital U into del E into capital U square. Okay, remember here this del E, it represents energy thickness. Okay, it represents energy thickness. So the as per our definition, this reduction in mass flow rate and this reduction in kinetic energy in this case, and reduction in kinetic energy by moving the plate, this should be same. So 1 by 2 rho into capital U del E into capital U square, it should be equals to integration 0 to del 1 by 2 into rho u capital U square minus small u square into dy. So finally you can cancel 1 by 2 1 by 2 to both side, rho and rho from both side, and you can divide this capital U on right side. So finally we will have the equation, the energy thickness del E equals to integration 0 to del capital U upon small u 1 minus capital U square upon small u square into dy. So this will be the equation for calculating the energy thickness del E. So in this way we have completed all the, or we had derived and seen all the different boundary layer thicknesses which can be asked in your exam. Okay, so in our next lecture we are going to discuss the boundary layer formation. Thank you.